Okay, welcome everyone. Let's settle down and get ready for our first presentation. Andrew, sit down, please. We have a special delivery feature today, and we are going to be hearing and seeing the research from two of the CAPS graduate fellows. The first one is going to be Yujie Wan, and she's going to be telling us about her research with the South Pole Telescope. Please take it away.
Thank you. Hi, everyone. I'm Yujie Wan. I'm a third-year grad student in the astronomy department, and I'm a current CAPS fellow. So today, I want to present on the transient detection project I've been working on for the past 2 years with SPT-3G, and I will focus more on the progress I've made last year. Okay, so big picture stuff. So transient events are important for us to study because they can offer great insights into some of the most energetic processes in the universe. But to fully understand them, we need to have multi-wavelength observations. Traditionally, transient surveys has focused on optical, X-rays, and other wavelengths. Well, for a long time, the millimeter wavelengths is mostly restrained to follow-up of events first in other wavelengths and remains largely unexplored. As for now, we have the South Pole Telescope, which is able to perform blind millimeter wave transient surveys thanks to its high sensitivity and cadence. And this opens up like windows for new discoveries. Here's a little overview for the instrument. It is a 10-meter diameter wide field telescope located at the Munson Scott South Pole Station in Antarctica. It is primarily a CMB survey telescope, and the observing strategy of regularly repeated observation of the same patch of sky make it also powerful for time domain science. It observes simultaneously at 90, 150, and 220. It has angular resolution of about 1 arc minute and field of view of 1.88 degree. So I'm going to show some results from previous transient searches with SPT-3G, which is the third generation camera. So the first systematic search for transient with SPT was conducted using 1 year of data covering 1,500 square degrees. This transient search has yielded 15 transient events, including 13 stellar flares from 8 flaring stars. Some stars flare multiple times, and also 2 extragalactic events, which are likely AGNs. So on the right shows the light curve for all the detected stellar flares, and on the right shows the associated stars from WISE with SPT contours overlaid on top. Till now, SPT has detected hundreds of transient events, with most of them being galactic flaring stars. As for stellar flares, there is a recent paper came out last year from our grad student, Chris Tandoy, presenting the stellar flare catalog from 4 years of survey data. So this catalog contains 111 stellar flares from 66 stars. So this is the color magnitude diagram for this population of stars. This is the magnitude versus distance plot for the same population. So the main point I want to make here is that the distance ranges from 10 to 1,000 parsecs, which means that those stars are all very nearby in our galaxy. So this kind of motivates the galactic plane transient survey. Before, we avoided the galaxies and looked towards the extragalactic sky. A few extragalactic sources have been found. Well, most of the detections are galactic flaring stars. So if we look towards the galaxy, we can see the Milky Way, where there are tons of stars and other interesting objects. I see a question, right? Yes.
I was a bit curious, like when you show the matching with Gaia, so all of those are local stars. But if you see the stellar mass distribution, which is also peaks near the galactic center, so is it possible that you find some of the transient, but there is no Gaia counterpart, and that might indicate that those are like very far sources?
Sorry, I didn't really pick up the question.
So What I'm suggesting is that maybe you don't see some of the counterparts in Gaia, and those might be like sources close to the galactic center or even farther distance. So is it like there is some scenarios? Is it like...
So for now, for all the transients we have found two, and they all have like Gaia associations.
All of them have counterparts?
Yes,
Okay.
and I think we will, for most of the time, we'll see Gaia association because it's pretty complete, I would say, right?
Okay, cool.
Yeah, so people have been making observations towards the galactic plane. Here are some examples, but they were all static continuum surveys and they were not in time domain. So this is the first time SPT looks towards the galactic plane, and it's probably the first millimeter wave galactic transient survey. From previous results, we are expecting to see a few stellar flares. And since this time we're looking towards the plane, not out of the plane, we're also hoping to see things we could not see before. So this survey will cover a number of known X-ray binaries, so we might be able to see that. We might also see cataclysmic variables, planetary nebula, magnetars, and maybe even things we don't know yet, which is very exciting. In parallel to this, there's also a kind of separate survey measuring the variability of Sagittarius star, which Paul Chichura, a grad student at UChicago, is currently leading. Okay, so let's get into the observing strategy of the galactic survey. The galactic field has been subdivided into 3 subfields, and here I'm showing the galactic fields on the sky. So the 3 blue boxes are the galactic fields, and the red dashed line is the galactic plane. The image on the right is a more zoomed in version, and it is rotated to galactic coordinates. The same thing here, the blue boxes are the galactic fields. The green dots is Sagittarius star, and the orange region is ASCAP galactic fields for comparison. So the field is limited by atmospheric loading, which determines how low we can go in elevation. And the field is designed to go as low as we can in elevation and also to maximize the overlapping area with the ASCAP survey. So when observing each subfield, the telescope started at the highest elevation and scanned back and forth at constant speed along constant elevation. After finishing each scan, the telescope takes a step in elevation and repeats scanning back and forth till covering up the whole subfield. For each observing day, we observe all 3 subfields, and we observe each subfield for about a dozen times. We started the survey in March 2023, and we came back to this field again in 2024, also in March for about a month. We choose to conduct the survey in March because that's the time when the main field got contaminated by the sun. So for the efficiency of the telescope, we choose to do our survey when the main field is not available. And for this year, the 2025 galaxy survey has started last week. So as we're speaking, the telescope is looking at the galaxy right now. So this is real data. This is the COAD map from all the observations conducted in the last 2 years. In the middle is the galactic plane, which you can see is super bright. Each subfield is about 3 degrees tall and 16 degrees wide. And the total area is about 98 square degrees. Till now, we have about 500 observations for each subfield, measuring intensity and also linear polarization at 90, 150, and 220. And if we combine all the observations, the co-added depths can reach 5.6, 6.8, and 23 microkelvin arc minute at the 3 bands respectively. So this plot is in 150, and if we combine all the 3 bands, we can make a pretty false color image. Let's zoom in on the galactic plane part, and you can see some of the famous objects here. Sagittarius star is the supermassive black hole at the galactic center. Sag B2 is the giant molecular cloud. You can also see 2 nebula, the Lobster Nebula and the Catapult Nebula. Okay, so now let's get into the data analysis part. I I'm going to skip a lot of the details to save time so I can spend more time on the results part later. So this is the general workflow for transient detection. It shows the basic idea how we go from the raw time order data to transient events. And I'm going to go through each step real quick. So the first step is generating individual map for each observation, and to do that, we use the map-making pipeline, which is similar to the one we use for other analysis, and we also tailored the pipeline to be more suitable for the galaxy observations. So the pipeline, what the pipeline does is that it converts the raw time order data taken by the telescope to maps for analysis later. And during the pipeline, there are many filtering steps applied on the TODs to reduce the noise. And after those filterings, we then weight and bind all the TODs in one observations to make an individual observation map. And here is an example. We then combine all the observation maps together to make the average map. We then subtract the average map from each individual map to make the difference map. And the differencing step is to remove the CMB background and static point sources, and ideally leaving only transient and variable sources in the map. We then apply a transient filter to maximize the sensitivity to point sources. And here's an example of a difference map after transient filtering. So you can see that the CMB has been removed, the static point sources have been removed, most of the emissions from the galaxy has been removed. You can see some weird artifacts at the position of Sag B2 and Sag J star. That's not real transients. The reason they're here is because they're super, super bright sources, and these are just signal leakage during the difference step. But other than that, the maps looks good and clean. This is the difference map movie in time order. This is just trying to give you a better sense of how the data looks like. And if you stare long enough, you can actually see things popping up by eyes. But we are not going to wait for that now. So those are the input file for the transient detection pipeline, and this is how the pipeline works. It runs through all the difference map in the same subfield in each year to try to find outlier pixels. And by outlier pixels, I'm defining them to be pixels that are above 5 sigma in both 90 and 150 simultaneously in one observation. And because there are signal leakage at bright sources, and those pixels can easily exceed 5 sigma, we mask those out before finding outlier pixels. And if we find one outlier pixels, we will go back into the map sets and extract light curves from all the observations in the same year. So we're requiring detection in both bands simultaneously because we want to reduce the number of false detections and also to speed up the pipeline. We're requiring 90 and 150, but not 220 because 220 is most noisy and it got affected by the atmosphere the most. So we don't use 220 for detection. But we will extract 220 light curves later if we find transients in the other two bands first. Right now, the detection threshold is 5 sigmas, which is pretty high. That's because we want to skim at the most obvious transients first. We will go deeper into the maps in the future. So what do we find? We find 2 transient events, one in 2023 and the other in 2024. So I'm not claiming that this search is complete or deep anyway. There are a lot more things we can explore in the future. I'm just saying till now we have found 2 obvious transient events. So here I'm showing the SPT light curve and thumbnails. This is the single observation light curve at 90 and 150. I'm not showing 220 because 220 is pretty noisy on single observation level. So in the light curve, you can very clearly see the transient events. And for both transient events, they have a time scale of about roughly a day, which is longer compared to stellar flare, which has time scale on the order of minutes. And for both events, there are about tens of observations that catch the events. And you can kind of see the rise here, and you can kind of see the fall here. And this is the thumbnail movie centered on the events at 90 and 150. This is just to show how the events evolve more intuitively. So this is the bin-like curve. So instead of showing the flux value at each observation, I'm showing the average flux value for all the observations conducted in the same day. In this way, we can increase the signal to noise, especially for 220 because it is noisy, and so we can learn something from it. I calculate the spectral index during the transient events. Here I'm showing the equation I use for calculating the spectral index between the bands. So spectral index of 0 means it's a flat spectrum where the fluxes are equal between the bands. Negative means a falling spectrum where the lower frequency has higher flux, and positive means a rising spectrum where higher frequencies has higher flux. Spectral index is a very important measurement because it can help us probe the emission mechanism for those events. So it's very interesting that the two events shows opposite spectral indices. And this is basically showing the same thing. This is the spectral index by observations. So this is showing the average spectral index, and this is like by each observation. On the bottom is the light curve, and on the top is the corresponding spectral indices. And it's basically the same thing. Source 1 has generally a falling spectrum, and source 2 generally has a rising spectrum. So we have the position of the sources in hand, so we can try to find counterparts in other surveys, and we have found pretty clear counterparts in Chandra, which is an X-ray survey for both sources. So here I'm showing the IRAC image, which is an infrared survey, as the grayscale background, and I'm overlaying the SPT and Chandra contours on top. So you can see the SPT and Chandra positions matches very well, and the positional difference are well within the pointing area of SPT. And if we trust the association, there are literature reports for both sources. So for source 1, there is a Swift paper on it, classifying it as a wide dwarf binary with a subgiant companion. They show lots of details, but their conclusion is that the donor star is a subgiant and the primary star is a wide dwarf accretor. For source 2, there is a whole paper dedicated to this source, and they show lots of evidence, and their conclusion is that this source is a white dwarf with a giant companion. So I think this is where we are at right now. We're trying to understand the emission mechanism, and we are currently preparing a publication. And I'm hoping the publication will be out by this year. So I think that is what I'm going to focus on for the next few months. And after the publication is out, here are the future plans. So I think the first thing I want to do is I want to go deeper. So right now, we are doing 5 sigma detections, and I want to go to at least 3 sigmas, which is what we usually do. And in this way, we can find more transients and also fainter transients. But to do that, we're also going to find lots of junks. So we need to think about a better way to differentiate between real transients and false detections. I think there are also discussions of doing the detection in one band and only, not in 2 bands simultaneously. So this way, we're not biased by spectral indices. Another thing I want to explore is long-term transient events. So the process I just described is pretty good at finding short-term transients. But to find long-term transients, we need to make coat maps on the time scale that we want to explore. So for the galaxy observation designs, in order to find the transients on time scale of months or years, we need to make yearly coat map. And here I'm showing the 2023 to 2024 yearly difference map, which is just basically the difference between the 2 yearly coat. And I did a very, very preliminary search for transients, and you can already see lots of sources there. So in the future, I really want to understand those sources, figure out what they are. My guess is that most of them will be AGNs, but we might be able to find something interesting there. And I think this is the last point. We want to improve the pipeline to make it faster. So right now, the current pipeline works on single observation level, which have timescale about 20 minutes or 2 hours, depends on what observation you're talking about. We are hoping to improve it to also work on single scan level, which have timescale about a minute, because we have this time resolution, so why not go faster? So here, the main panel shows a light curve that is extracted from the current pipeline, and the top panel shows a light curve that can be extracted from the future pipeline. So you can see we can improve the time resolution by a lot, and we can better characterize fast transients like stellar flares. Yes, I think that's it. Thank you very much.
We have time for questions?
Yeah, I have one point to make. Like, we have like 5 megasecond of XMM and Chandra time to scan the galactic center and the disk. So if you find counterparts in those sources, and if you look at the spectra of XMM and even sometimes Chandra, what happens is that if it is a wide dwarf, especially if it is a magnetic like an IP or polar, most often you see iron complex emission in the 6.6 to 7 keV band. So if you look at the spectra of X-rays, you'll be able to quantify like if it is a wide dwarf or not based on the spectral properties of X-rays. And
in a binary system, though, isn't the X-ray still dominated by the red dwarf?
sorry?
These are binary systems. So for a binary system, doesn't the red dwarf dominate the X-ray emission?
X-ray, no. It's coming from the shock of the white dwarfs.
Okay. We should talk more.
Yeah.
Yeah. Thanks for the comments.
I had a question about your second to last slide about the yearly coad. Have you checked that these also don't show up in the total coad? That they could be, sources that are always seen quiescently with SPT, but they just happen to be brighter. So rather than, I guess it's semantics, but I'd be interested if some of these do end up in some like point source catalog that Mel would make or something like that.
Yeah, I think because like Mel doesn't touch the galaxy, so we don't have a point source for the galaxy, and I think this is the 2-year data right now is what we have, and this is like dividing half by the half. So like I think all the sources I annotated here are not in the fully coad.
Okay.
No. Well, they're changing at least. They're changing. They're variables.
Any other questions? Go ahead.
Where do these pipelines run? What machines?
I'm using the SPT machine, Scott and Munson. So it's just like the computer, SPT computer.
Sorry, I missed where?
The
Where?
SPT computer and Chicago.
Oh, okay. All right, thanks.
But it's like supercomputer, so I think they also have nodes in NCSA, I guess. Yeah, in CAPS.
Any other questions?